Have you ever wondered what happens at the heart of a black hole, or even time itself begins to slow? Here, in the quiet of the night, we explore these silent giants of the universe with calm curiosity. Soft science, simple truths, gentle rhythms for rest and sleep. Stay with us until the end. This is the Sleepy BrainDose. When you listen to this journey, you may notice how easy it becomes to simply rest with curiosity, without any effort. By the end, you will understand what black holes are, why scientists call them the silent giants of the universe, and how they quietly shape the galaxies around them. You will hear how they form, how they bend light and time, and how we are able to know of their presence even though they hide in soft darkness. You do not need to remember every detail, for the rhythm of the words is enough. It is perfectly fine to let the knowledge pass gently, like breath, becoming part of the background of your own calm awareness. Black holes are regions in space where gravity has grown so strong that nothing can escape, not even light itself. When we say the word hole, it may sound like there is a gap, an emptiness, but in reality, a black hole is not a hole in the way we think of everyday spaces. It is a place where matter has collapsed into an extremely small volume, so dense that the pull inward is irresistible. Imagine this not as a picture, but simply as a soft idea, matter gathered so closely that the rhythm of its existence changes. The stars that once shone have reached an end where they can no longer push against gravity, and in that surrender, a black hole is born. You may notice how natural this is, like an exhale that follows every inhale, a cycle of creation and quiet collapse. To understand why black holes are called silent, it helps to reflect on the way they do not emit light of their own. Stars glow because their cores fuse elements, releasing energy outward in radiant waves. Planets reflect the light they receive, shining softly when illuminated by a star. But a black hole gives no such sign. Its surface is hidden behind what scientists call the event horizon, a boundary that marks the place beyond which no signal can return. This horizon is not a physical wall. It is a region in space-time itself, and passing it is like moving into a one-way flow, always inward, always deeper. In that sense, black holes are silent, because nothing they contain can speak back to us. No rhythm of light or sound can cross the threshold to our instruments. They remain unseen, yet profoundly influential. You may find it soothing to notice that even though the words black and hole suggest something harsh, the reality is calmer. These objects do not roam space like monsters. They rest where they formed, influencing their surroundings with gravity that is steady, predictable, and in its own way gentle. The orbits of stars around black holes can last for millions of years, following smooth curves shaped by spacetime. This is part of the safety of the cosmos. The same physical laws that guide an apple falling to Earth also govern the immense calm pull of black holes. Nothing is outside of rhythm. Even in their silence, black holes are part of the natural order. To think of them as giants is to remember their scale. A black hole formed from a star may be only a few kilometers wide, yet it contains more mass than our sun. A supermassive black hole, the kind found in the heart of galaxies, may weigh millions or billions of times more than the sun, filling a region larger than our solar system. Yet despite such mass, their presence is not chaotic. Their influence extends far, but smoothly, as gravity always does. Around them, galaxies spin, gas clouds swirl, and sometimes, as matter falls inward, great jets of energy are released. Paradoxically, some of the brightest beacons in the universe, all powered by the soft darkness of a hidden core. When we rest with this thought, it becomes clear that black holes are not so much fearful mysteries, but essential features of the universe. They are the silent giants that anchor galaxies, guiding their formation and evolution. They are teachers of patience, for they reveal themselves not directly, but through the motion of others. A star circling something unseen, a beam of light bending as though guided by an invisible hand, a rhythm in gravitational waves passing softly through space. All these are signs of a black hole. You may notice how gentle this is. Nothing loud, nothing demanding, only quiet influence, like the steady beat of a heart beneath the surface of life. It is helpful to remember that black holes were once only ideas. The concept arose from the mathematics of gravity, long before telescopes could detect them. At first, they seemed impossible, too extreme to be real. But the universe does not follow what feels comfortable. It follows its own laws. And as decades passed, evidence grew stronger, until the presence of black holes was no longer a question of belief, but of observation. Today, we know they are real, and that our own galaxy holds one at its center. You might notice how reassuring that is. We live in a universe where even the most profound mysteries can be touched by patient observation and simple reasoning. Listening in this calm way, you may sense how black holes bring together many threads of science: the life of stars, the bending of light, the flow of time, and the structure of space itself. They connect the very large with the very small, galaxies with particles, astronomy with physics. In their presence, questions of existence and order meet. And although those questions can feel vast, you do not need to hold them tightly. It is enough to let them drift through your thoughts, like clouds across a quiet night sky, passing slowly, without hurry. As you continue to rest with this topic, you may also notice the rhythm of your own breath. Just as the universe expands calmly, breath follows its own natural flow, in and out, without effort. This connection is gentle, but real. The same physical laws that describe stars also describe the air filling your lungs. In both, there is a rhythm, a slowness, and a kind of safety. Black holes, in their silence, remind us that even the strongest forces of nature unfold within patterns that can be understood. What you will gain, then, is not only knowledge of astrophysics, but also a sense of perspective. Black holes are reminders of scale, of slowness, of the way complexity arises from simple rules. They show that even in the deepest darkness there is order, and even in silence there is meaning. You may find this thought restful. The universe holds its mysteries not to frighten us, but to remind us that we are part of something vast, steady, and timeless. From here, we can begin to explore more deeply, to see how the very first ideas of black holes emerged in the minds of scientists centuries ago. Just as your thoughts flow gently now, those early concepts flowed from curiosity, shaping the calm beginnings of a story that continues to this day. When we look back at the history of black holes, it is gentle to remember that long before modern telescopes, long before space probes, even before Einstein, people already wondered whether light itself might one day fail to escape a strong enough pull. These were not yet called black holes, and the words space-time or event horizon had not been imagined. But the seeds of the idea existed. It is calming to see how knowledge often begins with a simple question asked quietly and then allowed to grow over centuries. In the late 1700s, the English philosopher and scientist John Michell wrote of dark stars. He suggested that if a star were large enough, with gravity so intense, even light would be pulled back. He reasoned this using Newton's law of gravitation, a law already familiar and trusted. If light behaved like tiny particles, then those particles could be slowed, stopped, and eventually trapped. Michell did not have the instruments to test this. Still, his thought was precise, and it planted a soft idea in the scientific rhythm of the time. You may find it gentle to reflect that one person, with simple reasoning and pen on paper, could imagine an object that would only be confirmed centuries later. Around the same time, the French mathematician Pierre-Simon Laplace considered a similar thought. He described stars so massive that light could not escape, and although he later set the idea aside, the trace of it remained. These early thinkers worked in a world where light itself was not fully understood. Was it a wave? Was it a particle? They leaned on the physics they knew, applying it calmly, step by step. It is easy to see how their questions reflected not drama, but steady curiosity. The universe was already showing hints that it held secrets far beyond the reach of their telescopes. For more than a century, the idea of dark stars rested quietly. The scientific world turned its attention to other discoveries: electricity, magnetism, chemistry, and later the vast expansion of astronomy. The suggestion that light could be trapped was considered more a curiosity than a prediction. And yet, like a soft breath held in the background, the concept did not vanish. It waited until new theories of gravity could give it fresh meaning. That new framework came with Albert Einstein in 1915. His general theory of relativity showed that gravity is not a force in the Newtonian sense, but the bending of space and time itself. Under this calm but revolutionary vision, matter and energy tell space-time how to curve, and space-time tells matter how to move. In this picture, the possibility of regions so curved that nothing can leave them became not only possible, but natural. The word black hole had not yet been coined, but the mathematics began to whisper that such objects must exist. Shortly after Einstein's equations were published, a German physicist named Karl Schwarzschild found a solution. Even during wartime, from the Eastern Front, he wrote down the mathematics of what would later be called a Schwarzschild black hole. His solution described the spacetime around a spherical, non-rotating mass. At a certain radius, now called the Schwarzschild radius, the escape speed would equal the speed of light. Beyond that, nothing could return. What Mitchell and Laplace had imagined, Schwarzschild had now given a precise mathematical rhythm. Einstein himself was hesitant. He thought nature would never allow such extreme objects to form. For decades, many shared this caution. They saw black holes as mathematical oddities, perhaps useful for thought, but not for reality. It is worth noting how often science advances in this gentle way. An idea is born, doubted, set aside, and then slowly revived. The slowness does not mean failure. It means patience, safety, and care. In this sense, the history of black holes is a story of rhythm, of thought moving forward and then pausing. Like the steady pattern of breathing got, as the 20th century moved on, the picture became clearer. New generations of physicists explored the mathematics of relativity, testing the stability of stars, examining how matter behaves when it collapses. They found that under the right conditions, collapse was unavoidable. Massive stars, when their fuel runs out, have no pressure left to resist gravity. The result, the equation said, was the formation of a black hole. Step by step, the scientific community began to accept that what had once been a curiosity might instead be one of the most important truths of the universe. You may notice how soothing it is to see the continuity here. Michel, Laplace, Einstein, Schwarzschild. Each one contributed without knowing the final shape of the idea. Together, their work formed a slow chain, each link resting on the next. There is a kind of gentleness in this, a reminder that knowledge does not need to arrive all at once. It can come slowly, like night unfolding into soft darkness, each star appearing one by one, The name black hole itself would not be spoken until the mid-20th century, when the American physicist John Wheeler used it in a lecture. Before that, scientists used terms like frozen star or collapsed object. The new name caught on because it was simple, clear, and direct. It invited people to imagine the unseen without complicated language. And so the silent giants finally had a name that matched their nature. In reflecting on these early ideas, it is calming to see that the path of discovery is not a straight line. It bends, pauses, and curves back, much like space-time itself. What began as a thought experiment in the 1700s grew into a central piece of modern astrophysics. Along the way, doubt and hesitation were not obstacles, but natural parts of the rhythm of progress. Just as breath includes both inhalation and exhalation, science includes both inspiration and caution. Today, when we speak of black holes, we often focus on the advanced details, the event horizon, Hawking radiation, or the images captured by telescopes. But beneath all of that lies this calm beginning, a time when the idea was nothing more than ink on paper, a question of whether light could be stopped. That beginning still holds a quiet beauty, reminding us that even the most profound truths can start softly, with a single thought. As we move onward, you may find it helpful to carry this sense of history, for it makes the next step gentler. From the first ideas of Mitchell and Laplace, through Einstein and Schwarzschild, we now arrive at the heart of the matter: how gravity itself, understood in relativity, creates the foundation for the existence of black holes. And in that shift, the story flows naturally into the calm curves of spacetime itself. When the early suggestions of dark stars had rested for more than a century, it was Albert Einstein who gave them new life. In 1915, he presented his general theory of relativity, and with it, gravity was no longer understood as an invisible force pulling objects together. Instead, it became the natural bending of space and time. This vision was not loud or sensational, but deeply elegant, as though the universe had always been quietly shaped by curves we had not yet seen. In Newton's view, gravity acted instantly at a distance. The Earth circled the Sun because the Sun's mass pulled it inward, while momentum carried it forward. That picture worked well for centuries, and in everyday life, it remains more than enough. But Einstein's insight was different. He suggested that space and time are woven together into a single fabric, space-time, and that massive objects curve this fabric around them. Planets do not so much feel a pull as they follow the straightest possible paths within a curved geometry. You may notice how this shift is gentle in its logic. It replaces an unseen tug with the calm image of lines bending and objects gliding along them. To imagine it, one might picture a stretched sheet with a weight placed at the center. Smaller objects roll inward, not because something drags them, but because the surface itself is curved. Yet even that picture is limited. Space-time has no edges, no fabric we can touch. It is more abstract, but also more precise. It tells us that gravity is geometry, and that time itself is part of the structure being shaped. It is worth reflecting that this is why Einstein's theory is still called a theory of relativity. Motion, distance, and time depend on the curved stage on which they unfold. Einstein's equations were not only elegant, they were powerful. Within them lay the possibility of extreme solutions, regions where space-time curves so sharply that paths inward never return. This was the mathematical foundation for what would later be known as black holes. At first, Einstein himself doubted that such extremes could exist in nature. But the equations did not hesitate. They accepted these possibilities calmly, without bias. In this way, mathematics was already whispering what reality would later confirm. Relativity also introduced the idea that time flows differently depending on gravity. A clock closer to a massive body ticks more slowly compared to one farther away. This is not illusion, but real difference. You may find it soothing to realize that time itself has rhythm, not absolute and rigid, but flexible, stretching and compressing according to mass and motion. The calm certainty of this has been tested many times, from satellites orbiting Earth to signals from distant stars. Every time, the results agree. Einstein's picture is accurate, but an especially gentle part of the story is how predictions of relativity matched observations. The bending of starlight during a solar eclipse, measured in 1919, provided early confirmation. When the sun passed in front of stars, their light curved slightly, just as the theory described. Newspapers announced it as a revolution, but beneath the excitement lay a simple truth. Light follows the geometry of space. It is easy to see how this extended the earlier thoughts of Michel and Laplace. What they imagined as light particles slowed by gravity became, in Einstein's vision, light traveling along curves drawn by spacetime itself. One can think of relativity as a language in which the universe writes its quiet story. Every planet's orbit, every falling apple, every beam of light crossing the cosmos is a sentence in that language. The grammar is geometry, and the punctuation is rhythm. Even the silent giants we call black holes are part of this same text. They are not exceptions, but natural expressions of the same rules. This perspective is calming, because it shows that nothing in the cosmos is outside order. You may notice another feature. Relativity does not only describe the motion of objects, but also the energy they carry. Mass and energy, bound by the equation E equals mc2 E equals mct E equals mc2, both curve spacetime. This means that stars, radiation, even invisible fields all contribute to the shape of the universe. It is worth pausing on this thought, for it connects everything. The warmth of the sun on your skin, the calm pull of Earth beneath your feet, and the invisible depth of a black hole all arise from the same principle. Different in scale, but joined in essence. Over time, physicists explored solutions to Einstein's equations. Schwarzschild's work, written during the First World War, showed that if mass is compressed within a certain radius, a horizon forms. This was the mathematical beginning of the black hole. Later, others extended the solutions, describing rotating black holes, charged black holes, and the subtle structures of their horizons. At each step, the mathematics grew, yet the rhythm of the idea remained steady. Gravity curves space-time, and extreme curvature leads to silence. It is calming to recognize that relativity has been tested not only in theory, but in countless experiments. The orbit of Mercury, slightly different from Newton's predictions, matched Einstein's equations exactly. Atomic clocks flown on airplanes and satellites confirmed time dilation. Gravitational waves, ripples predicted by relativity, were detected a century later, proving that even distant collisions of black holes send out quiet vibrations in spacetime. Each test is like a breath, steady and confirming, showing that the theory rests safely within reality. For our understanding of black holes, relativity is the essential foundation. Without it, the idea of light being unable to escape would remain only a curiosity. With it, the silence of black holes becomes not a fantasy, but a natural result of geometry. This is the calm gift Einstein offered, a framework where the most extreme objects are simply part of the universal rhythm. From here, the story leads us gently toward the stars themselves. For while relativity shows us that black holes can exist, it is the lives and deaths of massive stars that bring them into being. Just as breath follows breath, The theory flows naturally into the process of collapse, where matter yields to gravity and new giants are born in silence. To understand how black holes come into being, it helps to begin with the story of stars themselves. Every black hole begins as a star, but not just any star. Only the most massive have the conditions to end their lives in this extraordinary way. The quiet fate of smaller stars, like our sun, is different. They will one day expand into red giants, shed their outer layers, and leave behind a white dwarf, a dense, glowing ember that slowly cools. But for stars that begin life with far more mass, the journey is far more intense. Their final act is the collapse that leads to the birth of a black hole. You may notice that this difference depends not on mystery, but on the simple measure of mass, a steady property that guides the whole rhythm of a star's life. Stars are born from clouds of gas and dust that drift through galaxies. Over time, gravity gathers these particles, drawing them together until the density and pressure grow high enough for nuclear fusion to begin. In this fusion, hydrogen atoms merge into helium, releasing vast amounts of energy. It is this quiet but powerful reaction that causes stars to shine, their light traveling calmly across space, warming planets and guiding life. For massive stars, those with many times the mass of our sun, the fuel burns faster. Their light is brighter, their lifespans shorter. A star like the sun may live for billions of years. A massive star might shine for only a few million. It is worth reflecting on this. Greater strength can mean greater brevity, a reminder that in the universe, balance appears in many forms. Throughout their lives, stars are shaped by an equilibrium. The outward pressure of fusion pushes against the inward pull of gravity. So long as these two forces balance, the star remains stable. When fuel is abundant, the star shines steadily, each breath of fusion balancing each pull of mass. But as the fuel diminishes, the balance shifts. The outward pressure weakens, gravity gains the advantage, and the star begins to change. You may find it calming to think of this as a natural rhythm, not a disaster. Just as inhalation yields to exhalation, the life of a star yields to its ending dot in massive stars. Fusion continues far beyond hydrogen and helium. The core fuses helium into carbon, then into oxygen, neon, magnesium, silicon, and eventually into iron. Each step produces elements essential for planets and life. Without massive stars, there would be no carbon in our bodies, no oxygen in the air we breathe. It is easy to see that stars are not only distant lights. They are also forges, creating the material of life itself. Yet iron marks a turning point. Fusion of iron does not release energy. Instead, it absorbs it. At that stage, the star can no longer resist gravity through fusion. The rhythm that has held for millions of years falters, and collapse begins. The core of the star, now unable to support its own weight, implodes. Outer layers rush inward, and in many cases, the rebound creates a supernova, a bright, brief explosion that can outshine an entire galaxy. For a short time, the star that is dying becomes one of the brightest points in the sky. But beneath that light, something quieter is happening. The core continues to compress. If the mass is above a certain threshold, no known force can stop the collapse. Not even the pressure of neutrons, packed so tightly that matter resembles a giant atomic nucleus, can resist. At that moment, the star becomes a black hole. The boundary known as the event horizon forms, and the silent giant is born. You may notice how natural this process is. It is not random, nor violent in its essence, but a calm following of laws. Gravity pulls inward, pressure pushes outward, and when pressure can no longer keep pace, collapse is the outcome. And mathematics of relativity confirms this, showing that the curvature of space-time grows without bound once the critical density is reached. What appears to us as sudden is, in the language of physics, simply the next step. It is worth considering how central massive stars are to the universe. Without them, galaxies would not be enriched with heavy elements. Without them, planets would remain barren. And without their collapse, black holes would not exist. In this way, black holes are not separate mysteries, but natural heirs to stellar evolution. They are part of the same gentle cycle. Gas forms stars, stars burn fuel, fuel runs out, and collapse follows. Out of that collapse, the universe gains both silence and structure. Not all massive stars collapse directly into black holes. Some leave behind neutron stars, objects even denser than atomic nuclei, spinning rapidly and shining with radio pulses. Others may collapse quietly without a bright supernova, slipping into darkness almost unnoticed. The outcome depends on the mass of the core, the rotation, and other details. Yet the principle remains the same. When mass grows beyond the limits of pressure, gravity takes over completely. One can see in this pattern a reminder that the universe is consistent. Even its most extreme creations arise from rules that never waver. Scientists today study these processes not only with telescopes, but also with simulations, modeling the fates of stars across millions of years. In doing so, they learn how black holes seed galaxies, how supernovas scatter elements into space, and how cycles of birth and death maintain the rhythm of cosmic evolution. You may find it soothing to know that our own atoms carry the imprint of these ancient stars. The iron in our blood was once fused in the heart of a star that may have collapsed into a black hole. This connection is quiet, but profound, a reminder of how deeply life and cosmos are joined. The death of massive stars also teaches us about time. In everyday life, endings often feel abrupt. But in the life of a star, the ending is simply another phase, one guided by clear, steady laws. Just as a river eventually meets the sea, a massive star eventually meets collapse. This perspective can be restful, for it shows that even in endings, there is continuity. And even in silence, there is meaning. As we reflect on this process, it becomes clear that the path from star to black hole is neither strange nor unnatural. It is the calm fulfillment of gravity's promise. Matter gathers, shines, creates, and then returns inward. From that inward flow emerges the event horizon, the defining feature of every black hole. And so, from the lives and deaths of massive stars, the story leads us gently into the nature of horizons themselves, the quiet thresholds that separate what can be seen from what remains forever hidden. When speaking of black holes, one idea returns again and again: the event horizon. It is the defining boundary, the surface beyond which no signal can come back. In everyday terms, we might think of it as the edge, but in truth, it is not a physical surface. There is no wall, no crust of matter. The horizon is a property of space-time itself, a place where the paths outward all bend back inward. To cross it is not to strike anything solid, but simply to pass into a region where return is no longer possible. You may notice that this idea is both simple and profound, a horizon not of land and sea, but of events and information. The name Event Horizon reminds us that what is at stake is not objects, but happenings. Any event that occurs inside that boundary cannot influence the outside universe. If a star fragment falls past the horizon, its story ends there from our perspective. If light is emitted within that region, its journey never reaches beyond. For an outside observer, It is as though the horizon erases part of the universe's memory. It is worth reflecting that in this sense, the horizon is a veil of silence. Things continue within, but their echoes never emerge to someone falling toward a black hole. The experience of approaching the horizon would be strange but continuous. According to relativity, time flows differently depending on perspective. For the falling traveler, nothing special marks the crossing. There is no jolt, no sudden stop. But for a distant observer watching, the traveler seems to slow, their signals stretched into longer and longer wavelengths, fading into invisibility as they approach the horizon. One can see here the calm consistency of relativity. The same equations describe both the smoothness for one observer and the freezing effect for another. Each perspective is valid, each bound by the geometry of space-time. This duality often causes confusion, but it can be restful to remember that the horizon is not a contradiction, only a limit. It marks the place where definitions of inside and outside separate, and where different observers experience time in different rhythms. In our daily lives, we do not meet such boundaries, so they seem exotic. Yet they are natural outcomes of the same physical laws that guide everything else. You may notice how soothing it is to know that even horizons follow order. Without exception, scientists often describe the event horizon through the escape velocity, the speed needed to leave the pull of gravity. At Earth's surface, that speed is about 11 kilometers per second. At the sun's surface, much higher. At a black hole's horizon, the escape velocity equals the speed of light. Because nothing travels faster, not even light, nothing escapes. This explanation is simple, but it conveys the heart of the idea. The horizon is where space bends so fully that outward paths are sealed. The mathematics of horizons is subtle, but one can appreciate it without equations. Imagine all possible paths that light could take, radiating in every direction. Outside the horizon, some of those paths lead outward to infinity, carrying signals away. At the horizon itself, the outward paths curve so tightly that they hover, neither escaping nor returning. Inside, all paths turn inward. It is worth considering that this geometry defines the horizon more than any material structure does. The horizon is not built from particles, but from the shape of space-time itself. You may also notice how the horizon sets a natural boundary for knowledge. No observation from outside can reveal what happens within. We can describe the mass of the black hole, its spin, and its charge, because these properties affect the outside spacetime. But we cannot see details of the matter once it passes the horizon. This is why black holes are sometimes described as having no hair. They keep only a few simple properties, shedding all else. In this way, the horizon preserves mystery while still allowing predictability. From a calm perspective, the horizon can be seen not as a danger, but as an invitation to humility. It shows us that knowledge has limits, that there are regions of reality closed to outside view. Yet it also shows that these limits are precise and reliable. They are not shifting or unstable. They are part of the steady rhythm of the cosmos. To rest with this idea is to accept that not everything needs to be revealed, and that safety can exist even in the presence of silence. The event horizon also plays a role in thermodynamics. Stephen Hawking showed that quantum effects near the horizon create radiation, allowing black holes to emit energy slowly. This suggests that horizons are not absolute prisons, but boundaries where the smallest scales of physics leave their mark. The details are complex, but the idea is soft. Horizons are active surfaces, where the calm geometry of spacetime meets the gentle fluctuations of quantum fields. Over immense timescales, this radiation can cause black holes to shrink. It is worth thinking that even the darkest giants are not eternal, but change slowly, in rhythm with the universe. For astronomers, horizons are not only theoretical, they guide observation. When the Event Horizon Telescope captured the shadow of a black hole in the galaxy M87, what was seen was not the horizon itself, but its outline, the dark region where light is swallowed. Around it glowed a ring of matter, heated as it spiraled inward. That image, blurred yet profound, was a direct glimpse of space-time shaped to its extreme. One can see how the horizon, once only a mathematical concept, became a feature that telescopes could outline dot as we reflect on the horizon. It may be calming to notice its symbolic meaning as well. Horizons in our lives often mark transitions. The edge of the sea, the line of the sky, the point where vision ends. In black holes, the event horizon is similar. It is the line between what can be known and what lies beyond. Yet unlike earthly horizons, it is absolute. Once crossed, there is no return. This finality might sound harsh, but in the calm rhythm of science, it is simply another form of order. A horizon is steadfast, dependable, part of the universe's structure. To rest with the event horizon is to rest with boundaries. It tells us that nature has edges not because it is broken, but because it is whole. The silent giants of the cosmos are shaped by these edges, each horizon marking the point where silence begins. As we move onward, it is natural to wonder what lies within. If horizons hide events, what is at their center? With that thought, the story flows gently toward the singularity, the innermost region where our understanding of space-time itself begins to falter. At the very center of a black hole lies the most mysterious region of all, the singularity. It is the place where, according to our current mathematics, the density of matter grows without bound, and the curvature of space-time becomes infinite. In simpler terms, it is where the laws of physics, as we now understand them, break down. You may notice how unusual this is, for science is usually about rules and predictions. Yet here the rules themselves seem to falter. Still, even this faltering is calm in its nature. It does not erase order. It simply shows us the limits of what we know. The word singularity suggests a single point, but in truth the concept is more subtle. For a non-rotating black hole, the singularity is described as a point of zero volume and infinite density. For rotating black holes, the mathematics suggests a ring-shaped singularity. In either case, the meaning is the same. Our equations can no longer provide a complete picture. It is worth reflecting that this does not necessarily mean the universe itself becomes undefined. It may only mean our current theories are incomplete, waiting for a more unified description that can hold both gravity and quantum physics together. Physicists sometimes describe singularities as boundaries rather than places. They are not locations you could visit and describe in detail, but rather limits to our models, horizons for our knowledge. One can see this as another reminder of humility. Just as the event horizon shows that information can be hidden, the singularity shows that understanding can be unfinished. These are not failures, but invitations, openings for curiosity, spaces where future science may grow. It may be calming to remember that infinities in mathematics often signal that a new framework is needed. In earlier centuries, before calculus was refined, infinities seemed like barriers. With new methods, they became manageable, part of the language of science. In the same way, the infinities of singularities may not be permanent. They may yield, in time, to a more complete theory that blends Einstein's relativity with the quantum rules that govern the smallest scales. You may notice how gentle this possibility feels. The unknown is not chaos, but a horizon of future clarity. Inside a black hole, all paths curve inward toward the singularity. Unlike the horizon, which is a boundary seen from outside, the singularity is a final destination for anything that passes within. Matter falls inward, compressed beyond recognition, until the equations can no longer track it. From our perspective, the details of that process are hidden, shielded by the horizon. What remains to us are the outer effects, the mass, the spin, the pull of gravity. Everything else is lost to the singularity. It is worth considering how this simplicity mirrors nature's tendency to reduce complexity into order, even when we cannot see the inner details. Some physicists have suggested that singularities may not exist in the way the equations describe. Instead, the collapse of matter might be halted or altered by quantum effects, creating new structures we do not yet understand. Ideas such as quantum gravity, Planck stars, or loop quantum corrections are attempts to imagine what replaces the singularity when classical theories end. These are not yet proven, but they remind us that science is alive, still searching. You may find it soothing to think of this as part of the rhythm of knowledge. Each generation learns what it can and leaves space for the next to go further. Singularities also raise questions about time. If all paths end at the center, does time itself end there? In relativity, the answer is. The singularity is a place where time, as defined by trajectories of matter, ceases. To speak of after, the singularity has no meaning. This can sound unsettling, but in the calm perspective of physics, it is simply another boundary. Just as you cannot travel north of the North Pole, you cannot speak of time beyond the singularity. The language ends, not because reality fails, but because our concepts have reached their limit. You may notice how the singularity embodies both silence and possibility. Silence, because nothing about its interior can reach us. Possibility, because it invites new theories, perhaps new mathematics, that can one day describe it more completely. It is easy to see how this balance mirrors life itself. The presence of limits can spark the growth of new understanding. Astronomers do not observe singularities directly. They see only the effects of horizons and the motion of matter outside. Yet the singularity is still important, for it sets the black hole apart from all other objects. Stars may collapse into neutron stars, dense but still describable. Planets may compress, but never lose their structure. Only black holes, with their hidden centers, hold singularities. This uniqueness is part of why they fascinate scientists and the public alike. It is worth remembering that what makes them mysterious also makes them valuable, for mystery fuels inquiry. In daily life, it can be calming to consider that singularities remind us of scale. Our everyday experience is far from infinities, yet the same laws that guide a falling apple stretch all the way to the edge of knowledge at a black hole's core. One can see in this a kind of safety. Even at the boundaries of science, the continuity of reasoning holds. The unknown is connected to the known, not separate from it. The singularity is sometimes described as a paradox, but perhaps it is better thought of as a signpost. It marks the place where two great theories, relativity and quantum mechanics, both work beautifully in their domains, but fail to meet. The calm work of future science is to join them. When that happens, the singularity may no longer be a mystery, but simply another part of the universal rhythm. For now, we rest with the knowledge that singularities exist in our equations and shape the outer behavior of black holes, even if their interiors remain hidden. They are the silent centers of the silent giants, unseen but essential. From this quiet recognition, the story moves onward, toward the variety of black holes themselves, from stellar remnants, only a few, kilometers wide, to the supermassive beings at the centers of galaxies. Each type has its own rhythm, its own scale, and together they show us the full range of what black holes can be. When we speak of black holes, it is easy to imagine that they are all the same. Dark regions, hidden by horizons, silent in their pull. But black holes come in different sizes, and their differences tell us much about the universe. You may notice how comforting it is to see variety, even within something so extreme. Just as stars have lifetimes and classes, black holes too have their families, ranging from the smallest remnants of collapsed stars to the giants that anchor galaxies. First, and perhaps most familiar type, is the stellar black hole. These are born from massive stars that collapse at the end of their lives. Their masses range from a few times that of our Sun, up to perhaps a few dozen solar masses. In size, they are remarkably small, only a few kilometers across, smaller than many cities on Earth. Yet within that small region lies the mass of entire stars. It is worth reflecting on how density defines them. So much matter gathered into so little space that escape becomes impossible. Stellar black holes are the silent remains of once bright stars. Their final gift to the cosmos. Beyond these lie the intermediate black holes, a category more mysterious. They are thought to contain hundreds or thousands of solar masses. Evidence for them comes from dense star clusters and unusual X-ray sources. They are larger than stellar black holes, but smaller than the supermassive giants. One can see how they fill the gap, bridging the scale between individuals and galaxies. Scientists are still learning how they form, perhaps from mergers of stellar black holes, perhaps from the collapse of enormous early stars. Their existence is a gentle reminder that the universe often provides transitions. Not only extremes. At the largest scale are the supermassive black holes. These sit at the centers of galaxies, including our own Milky Way. Their masses reach millions or billions of times the Sun's mass. Their horizons stretch across distances larger than our entire solar system. Yet for all their size, they are not rare intruders. They appear to be common, perhaps even essential to the life of galaxies. You may notice how reassuring this is. The same silent giants that sound so mysterious also provide structure to the universe we live in. Supermassive black holes shape galaxies through their gravity and through the energy released when matter spirals toward them. Even though nothing escapes from within the horizon, the process of falling in can release extraordinary amounts of light and radiation. Some of the brightest objects in the sky, quasars, are powered by supermassive black holes feeding on surrounding matter. The paradox is gentle. The darkest objects can create the brightest displays. It is worth considering how this balance mirrors other rhythms of the cosmos, where opposites exist side by side without conflict. Scientists also speculate about another class, primordial black holes. These would not come from stars at all, but from fluctuations in the early universe, when density was uneven during the first moments after the Big Bang. If regions collapsed enough, tiny black holes might have formed, with masses ranging from very small to quite large. So far, no clear evidence has been found, but the possibility remains. You may find it soothing to remember that science often leaves space for the unknown, keeping doors open for future discoveries. The differences among these types remind us that black holes are not singular mysteries, but part of a wide spectrum. They are not exceptions to nature, but continuations of its patterns, emerging wherever mass and density cross critical thresholds. Stellar black holes arise from stars. Intermediate ones may grow in clusters. Supermassive ones form in galactic hearts, and primordial ones, if they exist, belong to the very dawn of time. Each type reflects the same principle, expressed at different scales. One can see in this pattern the universe's quiet consistency. Another way to consider their variety is by rotation and charge. A black hole can spin, carrying the angular momentum of the star or material that formed it. Spinning black holes, described by the Kerr solution, are not simply spherical, but have ergospheres, regions outside the horizon where nothing can remain still. Charge is less likely in astrophysical settings, but in theory, a charged black hole follows another set of equations. It is worth reflecting that even here, variety appears. Black holes are not uniform points of darkness, but subtle structures with properties that can be measured and compared from Earth. The way we encounter these types is not by direct sight, but by the motions and lights around them. Stellar black holes reveal themselves through the X-rays of infalling gas from companion stars. Supermassive black holes are traced by the orbits of stars near galactic centers. Quasars shine across billions of light years, marking the places where black holes feed with intensity. Each observation is indirect, but together they form a calm and clear picture. Black holes come in many sizes, each following the same gentle rules. It may be calming to notice how scale changes our perspective. A stellar black hole only a few kilometers wide can hold the mass of many suns, while a supermassive one can hold billions. Yet the same principles apply to both. Horizons form at the right radius. Singularities are hidden within. Space-time curves smoothly. This continuity across scale is part of the universe's safety. The rules do not break at larger sizes. They remain steady, guiding both the smallest and the largest. When we rest with this thought, the mystery becomes less intimidating. Black holes are diverse, but not chaotic. Their types are reflections of their origins, their sizes the measure of their histories. They do not wander at random, but rest in the places they formed, shaping galaxies, clusters, and even the flow of cosmic time. In knowing their families, we know the rhythm of the universe more deeply, from the smallest to the largest, from stellar remnants to galactic anchors. Black holes remind us that variety is part of balance. Their silence is not uniform, but layered, just as the night sky is not a single shade, but filled with stars of different brightness. And as we reflect on their sizes and kinds, it is natural to wonder how light itself behaves near these horizons. The gentle bending of beams, the curving of paths, the soft distortion of vision. In that thought, our journey flows calmly into the path of light around black holes. To understand the strangeness and beauty of black holes, it helps to pause with light itself. Light is the messenger of the universe. Everything we know of stars, galaxies, and planets arrives in the form of photons, tiny quanta that travel at the highest speed nature allows. In the quiet expanse of space, light normally moves in straight lines, undisturbed except by the slow redshift of cosmic expansion. Yet near a black hole, even light cannot ignore the extreme bending of spacetime. You may notice how profound this is. The very thing that defines visibility becomes subject to darkness, not because it is extinguished, but because its path is redirected inward. General relativity describes this gently but precisely. Light always follows the straightest possible line, but straight has meaning only within the shape of spacetime. Where spacetime is curved, the straightest path itself is curved. Around Earth, the bending is slight. Around the Sun, measurable but still gentle. Around a black hole, the curvature is so steep that light rays can loop, spiral, or be trapped. It is worth reflecting that this bending is not an external force, but the natural geometry of the cosmos. One can see this most clearly in the concept of the photon sphere. At a certain distance from a black hole, 1.5 times the Schwarzschild radius for a non-spinning hole, light can orbit in perfect circles. This orbit is unstable. The slightest nudge inward sends the photon spiraling past the horizon. while the smallest push outward lets it escape. But the fact that such an orbit exists is calming evidence of relativity's accuracy. Photons, normally racing across cosmic distances, can be held in looping paths by gravity's rhythm. From Earth, we cannot watch individual photons circle. What we see instead is the effect of this bending on light from matter surrounding the black hole. Gas falling inward is heated to extreme temperatures, shining in X-rays and visible light. As these photons try to escape, their paths are distorted. Some are redirected toward us, some are delayed, some fall back in. The result is a glowing ring, a bright halo of emission surrounding a dark interior. You may notice how soft this image feels. Light outlining absence, visibility defining invisibility. This is exactly what the Event Horizon Telescope revealed when it imaged the black hole in the galaxy M87. That picture showed a luminous ring encircling a shadow. That shadow is not the horizon itself, but the silhouette created by light paths bent around the hole. It is worth considering how remarkable this is. Humanity, on a small planet orbiting an ordinary star, was able to map the geometry of light near a supermassive black hole 55 million light-years away. Such achievements remind us of both the reach of knowledge and the quiet persistence required to gain it. Light near a black hole also demonstrates gravitational lensing, the way mass bends light from objects behind it. When a black hole passes in front of distant stars or galaxies, their light is curved, sometimes producing multiple images or rings. These effects, though subtle, can be measured. They turn black holes into natural lenses, magnifying background light. One can see how the silent giants, even in hiding, become instruments of observation, helping us see farther into the universe. For the light that ventures too near, redshift is another effect. As photons climb out of the steep well of space-time curvature, their wavelengths stretch. To an observer far away, the light appears redder, its energy diminished. At the horizon itself, the redshift becomes infinite. Signals fade entirely. This is why, to an external observer, matter falling into a black hole seems to freeze at the edge, dimming slowly into invisibility. You may notice how gentle this transformation is, not abrupt, but gradual, like a sound fading into silence as distance grows. It is also worth reflecting on the way light interacts with spinning black holes. Rotation drags space-time itself, a phenomenon called frame dragging. Light moving with the spin can travel farther outward, while light moving against the spin is pulled closer in. This asymmetry creates complex patterns in the glowing rings around rotating black holes. The brightness we see is not even, but tilted, shaped by the direction of spin. Once again, relativity's predictions match observations, giving us confidence in its calm precision. Thinking about light near black holes can feel abstract, but it connects directly to our everyday sense of vision. All sight depends on photons traveling to our eyes. To imagine a place where those photons cannot escape is to imagine a region where vision itself ends. And yet, rather than being frightening, it can be restful to recognize this as part of the universe's variety. Just as night follows day and silence follows sound, so too can darkness follow light, not as destruction, but as balance. You may notice how these ideas echo the earlier thought of horizons. The event horizon hides the interior. The bending of light paints the boundary. Together, they show that black holes are not voids, but structures with clear edges and behaviors. They are silent, yes, but never chaotic. Their influence on light is steady, predictable, and describable with equations that have been tested again and again. This reliability is part of the safety of science. Even when the subject is invisible, the laws remain firm. In the quiet rhythm of this understanding light becomes both teacher and witness. It bends, it fades, it circles, and in doing so, it tells us about the nature of space and time. Through photons, we see the shape of space-time itself. Through their absence, we learn the limits of vision. It is worth considering how profound this is. Light, which defines our sight, also defines its own end dot from here. The story continues naturally. If light can be bent and trapped, then what of other signals? Can the silence of black holes still be broken in different ways? The answer lies in the calm ripples of space-time itself, gravitational waves that carry information not as light, but as vibrations in the geometry of the universe. And so, gently, our attention turns from light to soundless waves, from vision to rhythm, as we enter the study of the silent music of black holes. When we describe black holes as silent, it is because no sound can travel through the vacuum of space, and no signal from within the event horizon can escape. They are quiet in the deepest sense, keeping whatever happens inside hidden. Yet silence does not mean absence. In their stillness, black holes shape the rhythm of galaxies, guide the paths of stars, and even send out waves that ripple across space-time itself. You may notice how paradoxical and calming this is. An object that swallows all signals still leaves the universe vibrating with its presence. For much of history, scientists assumed that black holes once formed were almost featureless. They had mass, perhaps spin, perhaps charge, but no way of interacting further. They seemed like dead ends in the story of matter. Yet relativity predicted something more subtle. When massive objects accelerate, they disturb spacetime, creating ripples known as gravitational waves. These waves are not made of light or particles. They are oscillations in the geometry of the cosmos itself, spreading outward at the speed of light. It is worth reflecting that even silence can have rhythm, carried not as sound but as pure geometry. Gravitational waves from black holes are most clearly produced when two of them orbit each other and eventually merge. For millions of years they may circle, spiraling slowly closer as energy radiates outward in these waves. At the end, in the final seconds, they collide and unite into a single, larger black hole. The outward vibration in spacetime travels across the universe. Billions of years later, detectors on Earth can register the tiny stretching and squeezing of space caused by this event. You may notice how gentle these signals are, the collision of two giants across unimaginable distances. Yet here they arrive as ripples smaller than the width of an atom. The first direct detection came in 2015, when the LIGO Observatory in the United States measured a gravitational wave signal from two merging black holes over 1 billion light-years away. The event lasted only fractions of a second, yet it confirmed a century-old prediction of Einstein's relativity. The detectors recorded a faint chirp, not a sound in space, but a translation of the wave into audio frequencies. It is calming to think that humanity, after so long, was able to listen to the silent dance of black holes. These discoveries have expanded quickly. Dozens of black hole mergers have now been recorded, each one adding to the map of the cosmos. By studying the frequency and amplitude of the waves, scientists learn the masses and spins of the merging holes, and even test whether relativity holds true under the most extreme conditions. So far, every signal has matched the equations. One can see here the steady reassurance of nature. Even at the edge of silence, the rules remain firm. Gravitational waves are not limited to black hole collisions. They also arise from neutron star mergers, from supernova, and perhaps even from processes in the early universe. But black holes are especially powerful sources. Their silence in light makes them difficult to observe, yet their merging sends out vibrations that no horizon can hide. It is worth considering how elegant this balance is, what they conceal in light. They reveal in rhythm. A study of gravitational waves has opened a new form of astronomy. For centuries, we learned about the universe only through light, visible, radio, infrared, X-rays. Now, with gravitational waves, we listen instead of watch. It may be calming to notice that this shift adds depth to our understanding. Just as hearing and sight together provide richer perception in daily life, light and waves together give us a fuller picture of the cosmos. There is also a poetic gentleness in the way these waves are detected. LIGO and Virgo use laser beams bouncing between mirrors kilometers apart. When a wave passes, space itself stretches and compresses, altering the path of the light by a fraction of a wavelength. The instruments are so sensitive that even the smallest tremors on Earth must be filtered out. And yet, with this fragile precision, we can trace the merging of black holes across billions of light years. You may notice how delicate science can be. Enormous truths measured by the quietest of shifts. The silence of black holes, then, is not absolute. They do not speak in light or sound, but they whisper in waves. These whispers tell us not only that they exist, but also how they live, merge, and grow. Over time, as detectors improve, we may listen to the earliest black holes, perhaps even to vibrations from the dawn of the universe. One can see how silence itself becomes a source of knowledge. If we are patient enough to hear God, it is worth reflecting that these waves are faint, not because the events are small, but because space is vast. By the time the ripples reach us, they have spread across immense distances. This faintness is part of their calm. Nothing urgent or overwhelming arrives. Only the gentlest of patterns, steady and measurable. In this way, even the collisions of giants become part of a soothing rhythm, woven into the background of existence. For those who rest with these ideas, there is comfort in knowing that silence is never truly empty. The universe holds layers of expression: light, gravity, waves, time. Black holes may appear mute, but they remain connected to the whole, their mergers resonating like distant chimes. You may notice how reassuring it is to think of the cosmos as musical, not in the sense of human melody, but in the broader rhythm of geometry and motion. From this perspective, black holes are not isolated voids, but participants in the universe's ongoing story. Their silence teaches humility, their waves teach patience, and together they remind us that even the most hidden places still belong to order. And as we move forward, it is natural to ask how else we can know of their presence. Beyond waves, beyond the absence of light, what other signs do astronomers use to detect black holes? With that question, our attention turns gently toward the methods of observation and the ways in which unseen giants can still be traced with certainty. Black holes are by their nature invisible. No light escapes them. No direct image of their interior can be captured. Yet despite this silence, astronomers have found many ways to know they are real. You may notice how gentle this truth feels. Invisibility does not mean absence, and quiet does not mean emptiness. By observing their effects on their surroundings, black holes reveal themselves. They cannot hide their influence on light, on matter, or on the rhythm of stars. One of the earliest methods comes from watching the motion of companion stars. In binary systems, two stars orbit each other. If one of them collapses into a black hole, the other continues to circle around the unseen partner. By measuring the orbit of the visible star, its speed, its path, its periodic changes in brightness, astronomers can deduce the mass of the hidden object. If that mass is too high for a white dwarf or a neutron star, the only remaining explanation is a black hole. It is worth reflecting that here, silence reveals itself through movement. The black hole is unseen, but the dance of its companion makes its presence clear. Another method involves the radiation from accretion disks. When gas and dust fall toward a black hole, they rarely do so in a straight line. Instead, they spiral inward, forming a thin disk. As the material rubs against itself, friction heats it to millions of degrees. The disk glows in X-rays and other wavelengths, bright against the darkness. Telescopes that detect high-energy light can spot these signals, even from thousands of light years away. One can see how the black hole, though silent, creates brilliance in its surroundings. The light does not come from the hole itself, but from the matter just outside its horizon, rushing inward and releasing energy. You may notice that this process is not chaotic, but ordered. The disk follows the rules of gravity and angular momentum, glowing in predictable patterns. In some cases, jets of particles shoot outward from the poles of the black hole, powered by magnetic fields and rotation. These jets can extend for thousands of light years, visible across the universe. It is calming to realize that even the darkest objects produce such structured displays. Silence at the core becomes light at the edges, a balance that is both elegant and steady. Gravitational lensing provides another path to detection. When a black hole passes in front of a background star or galaxy, its gravity bends the light, magnifying or distorting the image. Sometimes multiple images appear, sometimes rings of light, known as Einstein rings. Although subtle, these patterns can be measured. They tell astronomers not only that something massive is present, but also how much it weighs. It is worth considering how remarkable this is, the unseen revealed by bending what is seen. Closer to home, the most direct evidence of a supermassive black hole comes from the center of our galaxy. At the heart of the Milky Way lies Sagittarius A*. Astronomers have tracked the orbits of stars whirling around this invisible center. Their motions, mapped carefully over decades, show that they circle something with 4 million times the mass of the Sun, contained in a region smaller than our solar system. No other object could explain such density. You may find it soothing to know that even in the silence of the galactic core, science can read the rhythms of motion and uncover the hidden giant. Radio astronomy has also played a role. Some black holes emit radio waves from their surroundings, allowing large arrays of dishes spread across Earth to capture the signals. By combining data from many telescopes, astronomers can achieve the resolution needed to trace the structure of black hole environments. This is the method that eventually led to the first image of a black hole's shadow. It is worth reflecting on how collaboration itself mirrors the cosmos. Many small parts joining together to reveal something vast. Even without light, even without sound, black holes leave fingerprints. They shape the gas around them. They guide the stars nearby. They lens distant light, and they send out gravitational waves. Each method is indirect, but together they form a consistent picture. One can see how this consistency is part of the universe's calm. Different observations, different instruments, all pointing to the same truth. You may notice how these approaches remind us of life itself. Often, we understand something not by looking at it directly, but by observing its influence. We know the wind by the way trees move. We know time by the way moments change. In the same way, we know black holes by their effects, their quiet shaping of the cosmos. It is calming to realize that indirect knowledge can be as firm as direct sight. The detection of black holes is not only about confirming their existence. It also teaches us about their properties, their mass, their spin, their feeding habits, their growth over time. By combining X-ray observations, orbital studies, and gravitational wave detections, astronomers are building a map of black hole populations across the universe. It is worth considering how extraordinary this is. From a single planet, using instruments built with human hands, we can learn about objects billions of light years away. As the techniques improve, more will be discovered. Smaller black holes, hidden in quiet corners, may be revealed. Primordial black holes, if they exist, might show themselves through lensing or waves. And future telescopes, more sensitive and wide-reaching, will deepen our view of supermassive black holes in distant galaxies. You may find it restful to think of this progress not as a rush, but as a steady unfolding, like dawn spreading light across a horizon. In this way, the silence of black holes is never absolute. They do not shine, but they leave marks. They do not call out, but they can be traced. And through patience, astronomy has learned to hear what they do not say. From this point, the story flows naturally toward one of the most memorable achievements of recent years: the first image of a black hole's shadow, captured by the Event Horizon Telescope. That image, soft and blurred yet profound, was the culmination of many methods and decades of effort. For decades, black holes remained theoretical, inferred only from indirect signs. The orbits of stars, the brightness of X-rays, the faint whispers of gravitational waves. Yet no one had ever seen one, not even its outline. This changed in 2019, when a group of scientists working together across the globe revealed the first image of a black hole's shadow. You may notice how calm and steady progress can be. Years of patience, thousands of hours of observation, and the slow weaving together of data produced a picture that shifted our view of the universe. The black hole in question lies in the galaxy Messier 87, some 55 million light-years away. At its center sits a supermassive black hole with a mass about 6.5 billion times greater than the Sun. Around it, hot gas swirls, glowing as it falls inward. Light from this gas, bent and curved by the black hole's gravity, creates a distinctive pattern, a ring of brightness surrounding a dark interior. That dark interior is the shadow, not the event horizon itself, but the silhouette formed by light paths that cannot escape. It is worth reflecting that this shadow is the closest we can come to directly seeing a black hole dot to capture the image. Astronomers created the Event Horizon Telescope, or EHT. It is not a single telescope, but a network of radio observatories spread across Earth, from Hawaii to Spain, from Chile to the South Pole. By synchronizing them, scientists formed a virtual telescope the size of our planet. One can see how remarkable this approach is. No single instrument could achieve the resolution needed, but together they could. The method is called Very Long Baseline Interferometry, and it allows radio waves collected across the globe to be combined into one image. The observations took place in April 2017, with several nights of data gathering. Petabytes of information were recorded, stored on hard drives, and physically transported to central facilities because the volume was too great to send over the internet. Months turned into years as teams processed the data, checked for consistency, and refined algorithms to reconstruct the image. You may notice the rhythm of this work: slow, deliberate, careful, as if matching the patience of the universe itself. When the image was finally released in April 2019, it was greeted with awe. The ring was not sharp, but it was clear, a luminous halo around a dark core, just as relativity predicted. The size of the shadow matched the mass estimated from other measurements. The shape fit the curved paths of light around the horizon. It is worth considering how extraordinary it is that an idea born in mathematics over a century earlier appeared in the sky exactly as expected. This first image was more than just a picture. It was a confirmation that the mathematics of black holes describes reality. It was a demonstration that horizons and shadows are not abstract ideas, but features that can be measured. And it was a reminder of what collaboration can achieve. More than 200 scientists from across the world contributed, pooling their instruments, their skills, and their patience. You may notice how science itself mirrors the cosmos. Many parts, scattered across great distances, working together to form a coherent whole. The EHT did not only capture the outline of the shadow, it also revealed details about the spin and orientation of the black hole, about the brightness of the gas surrounding it, and about the magnetic fields shaping the region. Follow-up studies, using polarized light, showed that magnetic structures near the horizon are strong enough to launch powerful jets that extend for thousands of light years. One can see how the shadow is not an isolated picture, but the gateway to deeper knowledge about how black holes interact with their environments. For many people, the image carried emotional weight. Black holes had long been described as invisible, as unreachable. Suddenly, there was a picture, faint, glowing, imperfect, but real. It made the invisible visible. It is worth reflecting on how this can feel. Not dramatic, but quietly reassuring. The universe had not kept its secrets forever. With patience, careful methods, and global cooperation, we were able to glimpse what had once been hidden. You may notice that the image is not a single snapshot, but the result of averaging. Gas near a black hole moves quickly, changing from moment to moment. The EHT's methods reveal the stable features, not the transient flickers. This too is calming, for it reminds us that science seeks patterns that last, not just fluctuations. The shadow of a black hole is stable, enduring, part of the underlying geometry of SPAC, ETIME. Since that first image, the EHT has continued its work. In 2022, scientists released the first image of the black hole at the center of our own galaxy, Sagittarius A*. That story, which we will soon explore, carried its own challenges. Because the black hole is smaller and its surrounding gas shifts more quickly. Yet the achievement confirmed again that shadows are real and that horizons can be outlined by light. You may find it soothing to know that each new image strengthens the rhythm of knowledge, showing that patient observation leads steadily forward. The first image of a black hole was not the end of the story, but a beginning. It opened the door to black hole imaging as a new branch of astronomy. Future improvements to the EHT, new telescopes in orbit, and longer baselines will sharpen the pictures. One can see how, in time, we may watch the motion of gas in real time, tracing the dance of light around the horizon. Even the silence of black holes may become, in this way, a form of vision, dotting calm reflection. The first image of a black hole teaches us more than physics. It shows that invisibility does not mean impossibility, that patience can reveal what once seemed unreachable, and that the laws of nature remain steady across scales. You may notice how reassuring this lesson is, both for science and for life. From this point, it is natural to turn our attention closer to home. If M87 gave us the first picture, what of our own galaxy? At the heart of the Milky Way lies Sagittarius A*, a supermassive black hole whose influence we have traced for decades. And so, our journey flows gently from the distant shadow of M87 to the nearer silence of the giant at the center of our own celestial neighborhood. Among the countless discoveries of modern astronomy, few feel as intimate as the knowledge that our own galaxy holds a supermassive black hole at its center. This black hole, known as Sagittarius *, lies about 26,000 light-years from Earth, in the direction of the constellation Sagittarius. It is hidden behind clouds of gas and dust, invisible to ordinary sight, yet its presence is undeniable. You may notice how calming it is to think that even in the heart of our home galaxy, silence rests at the center, shaping everything around it. Sagittarius asterisk has a mass of about 4 million suns, gathered into a region no larger than the orbit of Mercury. To imagine such density is almost impossible, yet the mathematics of relativity confirms it. This mass guides the motions of nearby stars, pulling them into orbits that have been measured with exquisite precision. Over decades, astronomers have tracked these stars as they swing around the galactic center. Their paths, curved and rapid, reveal the gravity of something invisible yet immense. It is worth reflecting that these observations, patiently collected over many years, earned scientists the Nobel Prize in Physics. In 2020, the discovery of Sagittarius A* was gradual. In the early 1970s, astronomers detected unusual radio emissions from the galactic center. These signals, bright yet compact, hinted at something extraordinary. Later, infrared telescopes allowed scientists to peer through the dust and watch the motion of individual stars. What they saw confirmed the presence of a supermassive object. Nothing else could explain stars moving so quickly around such a small region. One can see how the pieces of evidence came together slowly, forming a calm and consistent picture. You may notice that Sagittarius A* is quieter than many other supermassive black holes. While some feed vigorously, shining as quasars or active galactic nuclei, our galactic center is relatively dim. The black hole consumes little material compared to its potential, and so it rests in a low state of activity. This silence may be part of why life thrives in our galaxy. A fiercely active black hole at the center could flood space with radiation. Instead, Sagittarius A* is gentle, exerting gravity without overwhelming light. It is worth considering how balance appears here too. A giant at the center, steady and calm, shaping the Milky Way without destroying it. The Event Horizon Telescope captured the first image of Sagittarius A* in 2022. Compared to M87, this image was harder to obtain. Sagittarius A* is smaller, and its surrounding gas moves quickly, changing on timescales of minutes. The data had to be carefully averaged to reveal the underlying structure. What emerged was again a bright ring encircling a dark core, just as relativity predicted. One can see in this echo of M87 a confirmation of the universality of black holes. Across distances and scales, the same rules hold. The same shadows appear. It may be calming to reflect that we are connected to this black hole. Our solar system, along with hundreds of billions of stars, circles the center of the Milky Way, drawn by its gravity. One complete orbit takes about 200 million years. In that time, continents drift, species rise and fall, and galaxies themselves evolve. Yet the black hole remains, a silent anchor around which all turns. You may find reassurance in this thought. Amid change and impermanence, some centers endure. Sagittarius A* also provides a natural laboratory for testing relativity. The orbits of stars near the center can be measured so precisely that tiny deviations from Newton's laws are revealed. The time dilation predicted by Einstein, the redshift of light climbing out of the gravitational well, the precession of orbits, all of these effects are observed. It is worth remembering that no other place offers such a close and clear test. Our galaxy's heart is both a mystery and a classroom, teaching physics through the quiet motions of stars. One can see how Sagittarius A ties together many themes. It shows that supermassive black holes are not distant abstractions, but real and present, part of the structure of our own home. It reminds us that galaxies are not only collections of stars, but also communities orbiting silent centers. And it demonstrates how patience and observation, watching stars move over decades, can reveal truths hidden for millions of years. May notice, too, that the presence of Sagittarius A asterisk raises questions. How did it form? Did it grow from smaller black holes, merging over time? Did it arise from the collapse of enormous early stars? Or did it form together with the galaxy itself, co-evolving as the Milky Way took shape? These questions remain open, awaiting future discoveries. The calm lesson here is that uncertainty is not failure. It is simply the next horizon, the next invitation to explore. Sagittarius A asterisk is not dangerous to us. Its gravity holds sway only in its local region. At Earth's distance, the pull of the Sun is far stronger than that of the galactic center. It is worth reflecting that even something with millions of solar masses can remain safely distant, its influence steady but not threatening. This perspective is calming. The giant at our center is part of the balance of the galaxy, not a source of fear. As we rest with this image, a quiet black hole glowing faintly with a ring of light. Hidden yet central, it becomes natural to think about its deeper effects. Beyond gravity, beyond orbits, black holes also affect time itself. Near horizons, clocks tick differently, and the rhythm of existence slows. From our own galactic center, the story flows gently toward the mysteries of time, and how black holes reshape it in ways both subtle and profound. Among the most fascinating aspects of black holes is the way they reshape time itself. Time, which we often take as steady and universal, is not fixed. In Einstein's relativity, time flows at different rates depending on gravity and motion. Near a black hole, this effect becomes profound. You may notice how calming it is to consider that even time has rhythm, stretching and slowing according to the weight of spacetime. Imagine a clock far from any strong gravity, ticking steadily. Now imagine another clock lowered toward a black hole. To the distant observer, that lower clock runs more slowly. Its seconds stretch, its rhythm lengthens. The closer the clock moves toward the horizon, the greater the difference becomes. At the horizon itself, from the viewpoint of someone outside, the clock appears to stop altogether. It is worth reflecting that this does not mean time truly halts for the falling object. From its own perspective, time continues normally. But relativity allows both perspectives to be true, each within its own frame. This difference is called gravitational time dilation. It is not only theory, it has been tested many times. On Earth, satellites orbiting high above tick slightly faster than clocks on the ground. Their signals must be corrected so that GPS systems remain accurate. These small differences are the same principle, applied in weaker fields. Near black holes, the effect becomes extreme. One can see here the consistency of nature. The same law guiding satellites also governs the deepest silence of horizons. You may notice how this bending of time changes our view of the universe. If you were watching matter fall into a black hole, you would see it slow down, redshift, and fade, never quite crossing the horizon. Yet from the matter's own perspective, the crossing is uneventful, taking place in finite time. This duality reminds us that time is not absolute. It is shaped by where you are, by how gravity bends the geometry of your path. It is worth considering how liberating this idea can be. Time is not a rigid ruler, but a flexible rhythm, woven into space itself. For black holes, this means that their influence extends beyond space, into the very pace of existence. Near the horizon, every process slows relative to the outside. Light redshifts, motion stretches, signals fade. The result is a calm barrier, not sudden but gradual, where communication ceases. From far away, The black hole appears to freeze its infalling matter, wrapping it forever in a shell of silence. Yet in the local experience, time continues, and the journey inward is finite. One can see in this contrast the beauty of relativity, two perspectives, each true, each consistent. Yet different. It may be calming to think of this effect in human terms. Our daily lives unfold on scales where time feels steady. But just as our perception of night and day depends on Earth's rotation, our perception of time itself depends on gravity's depth. Black holes remind us that what feels absolute is in fact relative, shaped by context. You may notice how gentle this realization is. We live in a universe flexible enough to allow many truths, yet consistent enough to hold them all together. The connection between black holes and time also touches on the future. A black hole can act as a one-way door to the end of time for anything that falls in. To the outside world, information appears suspended forever, while inside, the journey ends at the singularity. This raises questions about whether time itself ends there, or whether new physics will offer another explanation. It is worth reflecting that here we approach the boundary of knowledge, where patience and humility are needed. Some theories suggest that black holes may link to other regions of spacetime, perhaps even to new universes. Wormholes, though speculative, arise from the same equations. In such visions, time near a black hole could flow into entirely new directions. While these ideas remain untested, they remind us of the creative potential of physics. You may notice that even speculation here carries calm curiosity, not urgency. The unknown is a horizon, not a danger. From a broader perspective, black holes highlight how deeply time is tied to energy. Hawking radiation, which we will soon discuss, implies that black holes slowly evaporate over immense spans of time. For a stellar black hole, the time scale is longer than the age of the universe. For supermassive ones, it is unimaginably longer still. One can see how, in this sense, black holes teach patience. Their lifetimes stretch far beyond our imagination, reminding us that cosmic time is different from human time. That is also worth considering. How time dilation near black holes has entered human culture. Stories often imagine astronauts experiencing minutes, while centuries pass outside. While these tales dramatize the effect, the underlying principle is real. Time is relative, and black holes are the clearest demonstration. You may notice how even fiction, in its creativity, rests on a foundation of steady physics, not in quiet reflection. The lesson of black holes and time is one of perspective. To us, time feels steady, flowing evenly from past to future. But in truth, it bends with gravity, stretching and slowing. Near a black hole, this bending becomes extreme, yet it remains orderly, never chaotic. The rhythm of the universe includes many tempos, all part of the same composition. As we close this part of the journey, you may find it soothing to rest with this idea. Time is not fixed, but flexible, yet always consistent within its frame. Black holes show us the depth of this truth, turning seconds into eternities and eternities into moments. From here, the story flows gently toward another mystery. If time and matter both behave strangely near black holes, what happens to information itself? That question leads us to the paradox of Hawking's radiation and the quiet debates it has inspired. Until the 1970s, most scientists believed black holes were absolute in their silence. Once matter crossed the event horizon, it was thought to vanish from the universe's story, hidden forever in darkness. The horizon was a one-way boundary, and the singularity a final end. But then Stephen Hawking, applying the principles of quantum mechanics to the curved spacetime around a black hole, discovered something surprising. Black holes are not entirely black. They emit radiation, faint and slow, created by quantum effects near the horizon. You may notice how gentle yet powerful this idea is. Even the quietest giants are not eternal, but slowly change, breathing energy back into the cosmos. Hawking radiation arises from the now, fluctuations that quantum theory predicts in empty space. According to this theory, pairs of particles and antiparticles appear and vanish constantly, like soft ripples in the vacuum. Near a horizon, one particle can fall inward while the other escapes. The escaping particle carries energy outward, appearing as radiation. The inward partner reduces the black hole's mass. Over immense spans of time, this process causes the black hole to shrink. It is worth reflecting that this means black holes evaporate, not quickly, but with infinite patience, their silence dissolving into faint whispers of light. For a stellar black hole, the evaporation time is vastly longer than the current age of the universe. For a supermassive one, the time is even greater, beyond imagination. Yet the principle is profound. Black holes, once thought eternal, are finite. They live, change, and eventually vanish. You may notice how soothing it is to realize that even the most enduring things still follow cycles. Nothing lasts forever, but nothing is lost outside the rhythm of natural law. This discovery raised a deeper question, one that has become known as the black hole information paradox. In quantum mechanics, information about a system, its states, its properties, its arrangements, is never destroyed. It may change form, it may spread or scatter, but it persists. Yet if black holes evaporate completely, what happens to the information about everything they have consumed? Does it vanish with the whole? If so, this would break the rules of quantum theory. It is worth considering how delicate this tension is. Two pillars of science, relativity and quantum mechanics, meeting in conflict at the horizon. Some scientists argue that the information must somehow escape, encoded within the Hawking radiation itself. Others suggest it might be preserved in subtle structures at the horizon, or within new frameworks of physics not yet fully known. One can see that the paradox is not simply a problem, but an invitation. It points to the place where our understanding is incomplete, where future discoveries may unite gravity with quantum laws into a single calm theory. May notice that debates over the paradox are ongoing. Some proposals speak of firewalls, energetic barriers at the horizon that would preserve information, though this challenges the smoothness predicted by relativity. Others explore the idea that the horizon itself holds quantum hair, faint imprints of everything that has fallen in. Still others turn to holographic principles, suggesting that the entire volume of the black hole could be described by information encoded on its boundary. It is worth reflecting that each of these ideas, though unproven, represents the same rhythm of science, not rushing to closure, but patiently exploring, offering possibilities, letting time test them. For those listening calmly, it may be reassuring to know that the paradox does not threaten the fabric of reality. The universe continues in its rhythm. Stars burn, galaxies turn, life unfolds. The paradox exists only as a puzzle for theory, a gentle sign that our knowledge is not yet complete. You may notice how even this incompleteness is calming. It leaves space for wonder, room for curiosity, and a horizon for thought to approach. Hawking radiation also shifts how we imagine the end of the universe. If time stretches on beyond unimaginable spans, black holes may be the last luminous objects, slowly fading as they evaporate. In that distant era, when galaxies have dispersed and stars no longer burn, the quiet glow of Hawking radiation will remain, whispering the final rhythm of matter, returning to the void. One can see how this picture is not frightening, but serene. A universe completing its cycle in silence and light dot, it is worth reflecting on how Hawking's insight connects the smallest and the largest scales. Quantum mechanics describes the behavior of particles, relativity the behavior of galaxies and space-time. At the horizon of a black hole, these two meet. The paradox is not a flaw, but a bridge, showing where unification is needed. You may notice how gentle this perspective feels. Rather than breaking science apart, black holes draw its parts together. In everyday life, we rarely consider information as something physical. Yet in physics, it is treated with the same seriousness as energy or matter. The paradox of black holes reminds us that information, too, is part of the universe's order. Nothing can be erased without trace. Everything belongs to the ongoing rhythm. Whether stored in radiation, encoded in horizons, or preserved in new structures we have yet to imagine, information continues. This principle itself can be calming, for it suggests that nothing truly vanishes from the universal memory. As we rest with this paradox, it becomes clear that black holes are more than cosmic objects. They are laboratories for thought, places where the deepest questions converge. They remind us that knowledge has limits, but also that limits inspire growth. From here, our journey flows gently into that role. Black holes as laboratories, natural testing grounds for the union of relativity and quantum physics, guiding us toward a deeper understanding of the universe. When we think of laboratories, we often picture places filled with instruments, careful measurements, and controlled experiments. Yet, in a deeper sense, the universe itself is a laboratory. Black holes, though silent and unseen, are among its most powerful instruments for testing the laws of physics. You may notice how gentle this idea feels. Far from being only mysteries, black holes are teachers, offering lessons about space-time, matter, and the very structure of reality. In relativity, black holes represent the most extreme curvatures of space-time. Near their horizons, gravity bends light, slows time, and guides matter with perfect precision. These are the places where Einstein's equations show their full strength. To study them is to test relativity under conditions impossible to create on Earth. It is worth reflecting that every orbit we trace, every ripple of gravitational waves we detect, is a kind of experiment, showing whether the rules hold. So far, each test has confirmed relativity with calm certainty. Quantum physics also finds its frontier at black holes. Hawking's discovery of radiation showed that horizons are not silent but gently active, shaped by quantum fields. The paradox of information reminds us that our current theories are incomplete. One can see how black holes invite us to search for a deeper unity, a single description that holds both the large and the small. This search is patient, requiring decades of thought, but the direction is clear. Black holes mark the meeting place of the two great frameworks of science. You may notice that, in this sense, black holes are not only astrophysical objects, but also conceptual bridges. They connect gravity with quantum theory, thermodynamics with information, geometry with energy. Each connection is an opening, a chance to expand understanding. It is worth considering how remarkable it is that something invisible, hidden in soft darkness, can illuminate the deepest questions of physics. Astronomers continue to use black holes to test relativity. The orbits of stars around Sagittarius A*, measured to extraordinary precision, confirm predictions of time dilation and precession. Gravitational waves from merging black holes match the equations down to fine detail. The shape of shadows imaged by the Event Horizon Telescope fits exactly with theory. One can see how every observation so far has affirmed the calm reliability of Einstein's vision. Yet scientists also remain alert, listening for deviations. If any were found, they would point the way to new physics. It may be calming to reflect that black Holes also serve as laboratories for plasma physics and magnetism. The gas that swirls around them forms disks hotter than any furnace, shaped by magnetic fields into spirals and jets. By studying the patterns of light from these regions, we learn about turbulence, fields, and high-energy processes. These lessons flow back into understanding stars, galaxies, and even the early universe. You may notice how interconnected this is. What happens near a horizon teaches us about phenomena far from it. There is also the link between black holes and thermodynamics. Hawking showed that they have a temperature, an entropy, and a kind of thermodynamic behavior. This was surprising, because entropy is usually associated with disorder, with the number of ways matter can be arranged. For black holes, entropy is proportional to the area of the horizon, not the volume inside. It is worth reflecting that this insight sparked the holographic principle, the idea that information in a region of space may be described by data on its boundary. Black holes, then, became laboratories for entirely new ways of thinking about reality. One can see that even speculation about quantum gravity often turns to black holes. String theory, loop quantum gravity, and other approaches all test their ideas against the paradoxes of horizons and singularities. In this way, black holes quietly guide the search for a unified theory. They are like natural chalkboards, written upon by the universe itself, inviting us to read. You may notice how calm this perspective feels. The unknown is not an obstacle, but at Candace. It is worth considering that black holes also test our patience as scientists. Their timescales stretch far beyond human life. Their distances make them faint and slow to study. Yet the very act of waiting, of building instruments that gather data for decades, is part of the laboratory they provide. They remind us that not all experiments are quick. Some unfold with the slowness of stars, the rhythm of galaxies. And that rhythm, though long, is steady and reliable. You may notice, too, that black holes teach humility. They show us that our theories, however successful, are not final. At the singularity, relativity falters. In the paradox of evaporation, quantum rules are challenged. These are not failures, but invitations. They remind us that science is not about closure, but about continuing. It is worth reflecting that in this way, black holes are like teachers who never speak directly, but whose silence prompts deeper thought. For listeners, there is calm in realizing that the darkest objects are also the brightest beacons for knowledge. Black holes, invisible to the eye, become visible to the mind. Their gravity bends not only space-time, but also the direction of science itself, guiding us toward unity. One can see that this guidance is gentle, patient, and enduring. As we rest with this thought, it becomes natural to turn to another aspect of black holes. Not only their role in science, but also their role in culture and imagination. For while physicists see laboratories, the wider world often sees symbols of mystery, of endings, of unknown depths. And so, the story flows softly from black holes as teachers of physics to black holes as figures in myth, metaphor, and collective imagination. Black holes belong not only to physics, but also to imagination. From the moment the idea entered science, it began to echo in culture, in language, in metaphor. People who had never read an equation spoke of black holes as symbols of mystery, of disappearance, of the unknown. You may notice how natural this is. When faced with something invisible yet powerful, the mind reaches for images and stories to give it shape. In popular thought, black holes are often pictured as cosmic whirlpools, sucking everything down with violent force. This image is striking, but it does not reflect the calm reality. A black hole does not chase or pull at distant objects more than any star of the same mass would. Its gravity is steady, not predatory. Only very near the horizon does its unique character emerge. It is worth reflecting that myths often exaggerate, and yet they carry a kernel of truth. The sense of inevitability near the horizon becomes, in stories, a force of devouring. You may notice how language itself has adopted the metaphor. We speak of a financial black hole, an emotional black hole, a black hole of time. In each case, the phrase suggests something that consumes without return, something silent and draining. One can see how the scientific term, rooted in relativity, has traveled far into everyday speech, carrying with it a sense of depth and finality. Literature and art have also embraced black holes as symbols of the unknown. Writers imagine them as gateways to other worlds, as prisons beyond escape, or as mirrors of inner struggle. In cinema, they are often portrayed with swirling disks of light and dramatic pulls, visual shorthand for mystery. It may be calming to recognize that while these images differ from physics, they reflect the same human need to make sense of silence by filling it with story. In philosophy, black holes sometimes serve as reminders of limits. Just as horizons mark the edge of knowledge in space, they symbolize the boundaries of understanding and thought. You may notice how gentle this comparison is. Not fearful, but humbling. Just as no signal escapes the event horizon, no concept escapes the limits of reason. It is worth considering that in this sense, black holes are metaphors for humility, teaching that there are places we cannot yet go, truths we cannot yet see. Across cultures, darkness has often been linked with mystery and transformation. Night, caves, oceans, all have been symbols of the unseen. Black holes extend this tradition into the cosmos. They are the night at the heart of galaxies, the silence at the end of stars. One can see how their presence resonates with older human symbols, blending modern science with timeless imagery. You may notice, however, that in calm scientific perspective, black holes are not destructive in essence. They are stable, orderly, and predictable. The myths of chaos and devouring soften when we recall the truth. Black holes simply follow the laws of physics. They are part of balance, not outside it. To rest with this thought is to see how science can calm imagination, bringing gentle clarity to what might otherwise feel overwhelming. It is worth reflecting that black holes also inspire awe, not because they destroy, but because they connect. They tie galaxies together. They anchor the orbits of stars. They link relativity with quantum physics. In culture, they may be painted as voids, but in science, they are bridges between scales, between theories, between ideas. This duality is part of their power as symbols. As astronomy advances, cultural images shift as well. The first real pictures of black hole shadows, released in 2019 and 2022, softened many myths. Instead of terrifying whirlpools, people saw blurred rings of light, steady and calm, just as relativity predicted. You may notice how gentle this correction feels. Imagination still has its place, but it now rests alongside evidence. Fiction can dramatize, but science provides reassurance. Black holes will likely remain symbols for many generations, appearing in novels, films, and art. Their invisibility, their silence, their endurance make them fertile ground for metaphor. One can see how they stand at the intersection of fact and imagination, teaching both through physics and through story. They remind us of the unknown, but also of the patience with which knowledge grows. In this way, black holes live in two worlds, the world of equations and telescopes, and the world of language and myth. To blend these gently is to see them whole. They are both real objects of gravity and quiet symbols of mystery. You may notice how calming it is to accept both truths, science for clarity Imagination for meaning. From here, our journey nears its end. Having explored the science and the symbols, the silence and the light, it is time to close with reflection. Black holes, the silent giants, teach us not only about physics, but about perspective. And so, we move softly into the final summary, gathering what we have learned into a calm rhythm of understanding. As we come to the end of this journey, it is worth pausing to gather the many threads we have followed. Black holes, once only theoretical, have revealed themselves as real, consistent, and deeply connected to the universe. From the collapse of stars to the anchors of galaxies, from the bending of light to the whisper of gravitational waves, they show us how the laws of nature extend into the most extreme conditions. You may notice how soothing it is to recognize the consistency of these laws, holding steady even where space and time curve most strongly. We began with the origins of the idea, when scientists first imagined stars so dense that not even light could escape. Step by step, we traced how theory grew into observation, how equations found confirmation in the motions of stars, the radiation of disks, and the patterns of waves. One can see in this history a rhythm of patience, centuries of thought, decades of measurement, leading at last to the clear pictures of shadows outlined by light. It is worth reflecting that knowledge itself follows a calm orbit, circling steadily until it returns with clarity. You may notice how black holes, though invisible, are never absent. They shape galaxies, influence stars, and reveal themselves through the paths of light and the timing of waves. Their silence is not emptiness, but structure. Their stillness is not void, but presence. To rest with this idea is to see that the universe holds its mysteries gently, allowing us to approach them without fear. We explored their diversity. Stellar black holes, born from dying stars. Intermediate ones, rare and still uncertain. Supermassive ones, resting at galactic centers. And perhaps primordial ones, if the early universe left such seeds. Each type follows the same rules, each scale part of the same continuity. It is worth considering how this variety reflects the broader balance of nature, where diversity does not break order but strengthens it. You may notice, too, how black holes reshape our understanding of time. Near horizons, clocks slow, light stretches, signals fade. What seems steady in daily life bends in their presence. Yet this bending is not chaotic. It is precise, described by equations that match observation. One can see how relativity, tested again and again, holds firm even here. It is worth reflecting that this teaches us humility. Time itself is relative, and yet within that relativity lies consistency and calm. Hawking radiation added another layer, showing that black holes are not eternal. Over unimaginable spans, they radiate away, dissolving into faint light. This led to the paradox of information, a puzzle still unresolved, reminding us that knowledge has horizons too. You may notice how reassuring it is that science admits its limits openly, not as weakness, but as invitation. The paradox is a horizon for thought, a quiet boundary where future discoveries will emerge. Black holes have become laboratories for physics, natural experiments where gravity and quantum mechanics meet. They test relativity in the strongest fields. They test quantum theory at the edge of horizons. They inspire principles like holography that may guide us toward a unified understanding. One can see how even the darkest objects serve as beacons for thought, shaping the future of science. In culture, black holes carry symbolic weight. They appear in language, in stories, in art, as metaphors for loss, mystery, or transformation. Yet science gently softens the myths. Where imagination paints chaos, observation reveals order. Where fear imagines devouring, equations show balance. You may notice how the blending of fact and symbol enriches our view. Black holes are both real objects and cultural mirrors, both teachers of physics and figures of story. As we reflect on all of this, it becomes clear that black holes embody both mystery and clarity. They hide, yet they reveal. They consume, yet they also give. They stand at the boundary of knowledge, yet they invite us forward. It is worth resting with this paradox. The silent giants of the universe teach us not by what they say, but by the quiet patterns they leave behind. You may notice how the story of black holes is also the story of human patience. No single observation, no single theory was enough. It took centuries of thought, decades of instruments, teams spread across the world, and the persistence to wait for faint signals. One can see in this effort a reflection of the same rhythms we study: steady, slow, enduring. The universe reveals itself not in haste, but in time. At the heart of this journey lies a simple reassurance. The cosmos, though vast and sometimes silent, is knowable. Its rules do not change from place to place. Its rhythms remain steady across scales. Black holes, far from breaking those rules, confirm them at their most extreme. It is worth reflecting that this is the deepest comfort science can offer. Not that all mysteries are solved, but that the universe is consistent, trustworthy, and open to exploration. And so, as we close, you may find it calming to return to the image of a black hole's shadow, a soft ring of light encircling a silent core. It is both an ending and a beginning, both a boundary and a doorway. It reminds us that even in darkness there is structure, even in silence there is rhythm, even in the unknown there is safety. Let this thought rest with you as you drift into quiet. The silent giants of the universe are not threats but teachers, showing us balance, patience, and the enduring calm of natural law. In their presence, time slows, horizons form, and knowledge deepens. And as you breathe gently, you may notice that this rhythm of calm science, steady, soft, and endless, can carry you into rest, just as the universe carries its stars around the silent centers of galaxies. Thank you for sharing this peaceful time with the sleepy BrainDose. May the calm rhythm of science carry you gently towards sleep, with curiosity still softly awake. If you enjoyed this quiet journey, you're welcome to like, subscribe, or share a thought in the comments. Join us again soon for another gentle exploration of the universe.